All right, I've got the top of the hour, and I want to welcome everybody to our NCAT monthly webinar. That is from research to implementation. It's our webinar series. Today, we've got a fantastic topic, which is perpetual pavements with alternative base layers. There's some really exciting work that has been done in the partnership with NCAT and with Virginia, specifically VTRC. That's really, really neat work that's happened there. So let me introduce everybody, and then we'll jump into our normal layout that we do here of having NCAT tell its story, and then somebody out there in the industry that's utilized that technology in practice. So Nathan Moore, he's an assistant director here for the test track research at the National Center for Asphalt Technology. He's responsible for seeing all of the track research programs. Prior to that role, Nathan served as a lab engineer for 8 years in the NCAT lab, specializing in balanced mix design, pavement friction. He holds a bachelor's and a master's degree here from Auburn University in civil engineering. He's licensed in Alabama, and he has got kids that just started school again this fall, and their pictures on social media looked great as his wife posted those out there. Dr. Suri Gadaganti is an assistant research professor here at NCAT as well. He's got 8 years of experience in asphalt materials, pavement design, thermal modeling, and life cycle assessments. He earned his PhD here from Auburn University, and his research there focuses on life cycle analysis, sustainability, pavement materials, pavement design. He is a busy guy, got married about 18 months ago, bought a new house, and I saw he just signed up to go to the gym tonight, which I'm super excited about. Then we have Brian Diefendorfer, who is a principal research engineer at the Virginia Transportation Research Council, or VTRC. Specializes in pavement recycling, asphalt pavement design, non-destructive pavement evaluation, and pavement stabilization. He got a plethora of degrees, all in civil engineering, from Virginia Tech. At VTRC, he continues to lead innovative efforts in sustainable and cost-effective pavement solutions, helping translate cutting-edge research into practice. Brian and his wife Stacy are very busy chasing some very active teenage boys, so they're always out there chasing that down. As always, please make sure that you mute yourself and listen in to what our presenters have to say. We ask that you put any questions that you have in the chat box. I'll go ahead and pop that up for everybody, and we'll go from there. Nathan.
Great. Thank you, Travis. All right, so you guys know the drill, but for anyone who's new, I'm going to introduce our topic, very brief, a slide or two, broadly introducing the topic and how NCAT got involved in specifically in this case, perpetual pavements with alternative bases. We're going to focus more on the base material side on the introduction. Then I'm going to kick it over to Suri, where he'll dive into a much deeper dive into NCAT's history and the research that we've done related to CIR, CCPR, full depth reclamation, things like that. But then we're going to kick it to Brian being one of the experts really out there in the industry on this topic. And then we'll have a time to answer questions, and then we'll close out. I will reiterate what Travis said. If you have questions, please go ahead and get them in the chat box as soon as you come up with them. Some of them we will just answer on the fly via the chat, and then maybe have a discussion afterwards on that. But it's always nice to kind of see those questions flow in. So, alternative base layer history at NCAT. This really started, at least from an NCAT perspective, back in 2012. This is whenever VDOT started to do some of their full depth reclamation and CCPR work at the track. We also did a CCPR section on Lee Road 159, and for those of you who are familiar with our preservation work, that is our low volume preservation site. That road heading in and out of a quarry. So I'm showing you a picture here of the cement stabilization process. But we did a lot more. We've done a lot more recycled base sections since then. In 2015, we did CCPR and CIR out on US 280, which is our high volume preservation site. We also did CCPR through a hot mix plant. It wasn't hot; we ran it cold, but we retrofitted an Aztec double barrel drum in order to be able to run CCPR, splitting the wrap between cold feed, calibrated aggregate cold feed bins, but also wrap cold feed bins, and metering cement in through the baghouse auger return. And so we took a break in the 2018 cycle. We continued a lot of the work that Surrey's going to talk about in a moment, and then we did more CCPR work in 2021 for Virginia DOT, and then again in 2024. And then we've also recently, back in 2021, and we put some sections on our off ramp, looking at rejuvenated CCPRs. So these layer types have a very proven success track record, both here and out there in the industry. What I'm showing you here is a plot that Surrey is going to talk about more in a moment. These are the first three sections we did for Virginia back in 2012, where we were looking at 5 inches of CCPR with 4 inches of asphalt on top, 6 inches of asphalt on top, but then also FDR and CCPR with 4 inches of asphalt, and seeing different strain responses. And ultimately, this is how you characterize perpetual pavements. And as Surrey talked about in last month's webinar, the Willis limit and critical microstrains threshold values in order to determine whether a pavement is perpetual or not. You do that same type of analysis here. In 2021, that's where I don't think Surrey's going to talk very much about that today, but just to give you an idea, in an effort to really push this technology forward even more and looking at high performance CCPR, that's where we actually had different types of modified or polymer modified emulsions or rejuvenated CCPR sections to look at how good can you make these base layers. This is incredibly pertinent for contractors and agencies who have urban areas that have tons of wrap surface. But ultimately, as the premise of this webinar and then last month's webinar is perpetual pavements. Perpetual pavements require strong bases, and you can achieve that obviously through hot mix layers, but also through alternative base layers. So with that, I'm going to turn it over to Surrey. I'll stop sharing my screen.
Thank you, Nathan, for the introduction. I think you set a really good foundation for my slides, whatever going to come in. So I just want to briefly touch again on what we covered in the last webinar session so that there is a transition happening between what we saw last session and last month or this month. So pre-1950s, if we talk about the pavement thickness design, if we will, the before 1950s, the thickness design was pretty much based on the experience of how many inches of asphalt or base layer we're going to put in our pavements. But between that 1950s and 1960s, there was this big ASHO road test happened outside of Champaign in Illinois, which basically gave us the 1993 ASTO design methodology altogether, which was modified in 1993, but that's the basis of the ASTO empirical design methodology. That's what we implemented in the 1960s, but in early 1980s, through NCHRP efforts, we started thinking not just from an empirical standpoint, but also more from a mechanistic empirical standpoint, where we also started looking at stresses and strains in the pavement and relating them to the pavement thickness and the distresses all along. 1990s, that's when the big NCHRP MEPDG work happened, which basically is the big research project from which MEPDG design methodology came in. And in 2000s, we saw the implementation of MEPDG and still adopted by several state devotees. One example is Virginia, where Brian is from, where they adopted MEPDG guidelines. But what's happening alongside with the MEPDG implementation in 2000s was the concept of perpetual pavements. What are perpetual pavements and how those are going to be different from a conventional pavement? The concept of perpetual pavements comes from Europe originally, like last time we talked about, and then adopted in California, then in Colorado, then in Illinois. But now through Asphalt Pavement Alliance, perpetual pavements promotion that perpetual payments are being adopted by several state devotees. But what are these perpetual payments? So at the end of the day, what we're trying to do with perpetual payment design concept is trying to limit the bottom of fatigue cracking. So we're trying to make sure that payment section that we're designing is not going to see any bottom of fatigue cracking in future, or at least for the next 50 years, so that if we are arresting the bottom of fatigue cracking and the deep structural rutting on the subgrade, you don't have to go back and do a complete reconstruction or a big rehabilitation thing. Only thing that you need to do is go back every 12 years or 10 years and just mill and fill the surface layer where you basically have aging related issues. So that's the whole concept of perpetual payment is we are trying to arrest or control the bottom of fatigue cracking at the asphalt layer by controlling the tensile stresses that we're producing through traffic loading, and also control the deep subgrade rutting, or the structural rutting, what we call, on the top of the subgrade by controlling the vertical strains caused by the traffic on top of the subgrade. So that's basically the perpetual payment concept. But what are we seeing from an NCAT side of the story, or NCAT implementation side of the story, is from 2009 onwards, through Dr. Richard Willis's work and Dr. David Tim's work, what we observed before that point, before 2009, there is endurance limit concept for asphalt mixtures. Basically, if your strain is low enough below that endurance limit, however many number of fatigue cycles or trafficking that you're applying, it basically is not going to cause any fatigue damage to that material. And before 2009, the general understanding was that number is about 70 to 100 microstrain for asphalt mixtures. But through the work that happened between 2009 and 2015, with the test track sections that you're seeing on the screen, N1 to S11, what Dr. Richard Willis and Dr. David Tim, what they observed is it's not a single value, or it's not a single strain, because your pavement is going to experience different temperatures throughout its life and different traffic loads on that top of the pavement. So which are going to, at the end of the day, are going to result in different tensile strains at the bottom of that AC layer. So it's not a single value that you always see. It's a distribution happening over the time. So the second column of this table is what the strain limits that we came up with in 2009, because we instrument all of our test sections with, or all of our structural test sections with strain gauges at the bottom of the AC layer, so that we basically could measure how much tensile strain those sections are going through over the trafficking period. And by analyzing all of that, Dr. Richard Willis, this is what we call Willis limit, came up with this distribution. If you see the dotted line on this one, if the strain values for the section that you're looking at are falling onto the right side of that dotted line, those are going to be not perpetual, because those are causing, or that structure itself is causing too much of strain than what it is desired according to the Willis limit. So you're going to see a bottom of fatigue cracking for that pavement. But if the strains are falling to the left side of the curve, where basically the strains are lower than the Willis limit, that is when you're not, all the strains that you're producing with traffic on that section are much lower than that is required to fail by bottom of fatigue cracking. So those are going to be perpetual. But if you see all the sections that we have been analyzed till now for the perpetual concept were granular basis, conventional granular ag basis, not recycle basis. But the question is, can we use the same limits? Can we use the same Willis limit for a recycle basis? For example, if somebody is doing an FDR and a CCPR or a CIR, can we still use the very same concepts of, or the very same Willis limit, Willis strain limit, to characterize if a pavement is going to be perpetual and not perpetual, if we're designing them or if we're constructing them with alternate base materials or recycled materials, in short. That is more important right now in today's world, is just because we see very few projects that are either widening projects or new construction, right? Because most of our road network has been built already. So most of the work that we're seeing these days as Nathan mentioned is mostly maintenance and rehab type of works, and especially if a pavement is deteriorated structurally, if you see the alligator cracking right here, in order to address the deep structural failure, we end up adopting uh, a major rehabilitation strategy. And we do have a whole big tree or bunch of different maintenance and rehab activities, that options that we have, depending on the level of distress and the type of distress. But what we're going to concentrate mostly today are going to be related to the structural rehabilitation. And within structural rehabilitation, we have different options of reconstruction, but also the recycling, where we are basically using the distressed material, we're milling it off and reusing and making a recycled base out of it, or a much more stronger base than a conventional granular base. So we're gonna pretty much gonna talk about this one today. A quick 101 on recycling is, it's basically we're trying to use the distressed material or the pavement section and mill it off and use all of those recycled material and make a new product out of it, or a new base out of it. I mean, depending on the people that you're talking with, some people would say it's 100% recycled material, but you're still adding some new material to it, right? So you're basically milling off that distressed wrap material, and you're adding 2 to 3% binder, either by emulsion technology or by foaming, depending on whether you're doing it by foam or emulsion. And when you're doing it by foam, you're also adding some kind of active filler like cement or lime to give that initial strength to the material. But at the end of the day, if we are moving away from reconstruction, but using recycling, we would end up saving a lot of dollars, obviously, because 97% of the material is just coming from the very own distressed pavement itself. And especially if you're using cold recycling techniques, where we're not heating the material, but at room temperature, at ambient temperature, we are saving a lot of energy, thereby emission reductions at the end of the day. And one interesting point is, especially if you're when somebody's doing a CCPR, cold central plant recycling, which I'll be touching a little bit in a couple of slides from now, is we could use the capital investment that's already available. So we don't have to have a mobile plant. I mean, the current practice is to have a mobile plant off-site where the wrap millings are coming in and we're mixing in the mobile plant. But we did some work where we used the double barrel plant to produce the CCPR mix itself, the existing conventional asphalt plant. That's what Nathan just mentioned about for the work that we did in 2024, where we used the double barrel drum basically to mix all of that material up. All right, what is the difference between all the recycling technologies out there? We have cold in place recycling. Basically, the name itself says it basically everything is happening in place. So the milling of the distressed layers, we only do this or treat the bound layers. So we're not talking about granular beneath the asphalt layers. We're milling the asphalt layers or failed asphalt layers and mixing that with emulsion or foam, and paving it back and compacting it. And everything is happening on site in place. So that, as the name suggests, and everything is happening at a cold temperature. We have hot in place recycling as well, but we're going to pretty much talk about the cold in place recycling in this presentation. And it's usually 2 to 3 inches thick, this CIR layer itself. And we also have cold central plant recycling. Again, it's similar to that, the earlier slide, what you saw, but only difference is we are taking all that milled material to a mobile plant where we are mixing it with an emulsion or a foam or an active filler, basically making a new mix out of it, and then bringing that back to the paving site, paving it like a typical HMA with a paver, and compacting it to make a really good, strong base, basically a stabilized base with emulsion of foam at the end of the day. Full depth reclamation, it's a bit different from the earlier two cases. This is where we also correct or recycle some of the granular material as well. Mostly all the bound layers, the HMA layers on top, along with the base layers. Sometimes it can even go a few inches into the subgrade as well, where we are basically stabilizing with the lime cement, and it's usually 10 to 12 inches thick, and then basically we are making a good strong base out of it. But that's the general information. But what kind of relevant findings what we got from the test track? So let me quickly shed a little bit of light on what we found from the track findings itself. As Nathan mentioned just earlier, in 2012, Virginia Devotee, Brian, they basically sponsored 3 test sections at the test track to look at how the CCPR and FDR materials are performing, or how good they are performing, to look at specifically 3 different cross-sectional types. One, N3, which has basically 3 different layers of asphalt concrete with 6 inches in total, and a 5-inch CCPR layer, which is sitting on top of a conventional granular base, 6 inches and subgrade. The next section, N4, is only different in terms of only 2 inches lesser asphalt concrete compared to N3. So now we're talking about 4 inches of AC on top of 5 inches of CCPR on top of conventional granular base and subgrade. While S12 consists of 4 inches of AC, 5 inches of CCPR sitting on top of 8 inches of FDR. So this is even stronger cross-section that we're seeing for S12. So the whole idea for these to understand how these are going to perform, and these test sections were built in 2012. But how are they performing, or how did they perform? Probably is the best word, because all these sections went offline last research cycle. So let me give a quick understanding of like how did they perform. So the section N3 with that 6 inches of AC and 5 inches of CCPR, that had no cracking for the first 2 research cycles, what we saw of that section, which saw about 20 million easel traffic applications. And Virginia decided to take that section out. It went offline, so we don't have any data after 20 million easels. But only thing that we know is it performed well until that first 20 years without any cracking. And the section the section S12 with the FDR layer, which is the strongest out of all 3 of them, went through 3 different research cycle of trafficking. And after 30 million easels, it did not have any kind of cracking. And we classified this section as Perpetual. I'm gonna touch base on why we are started calling that as Perpetual in terms of strain information. But it went through 30 million easels, nothing happened. 30 million easels is basically, you're talking about on a typical highway application, a very high traffic load, like high traffic volume interstate. Probably that's about 35 to 40 years of trafficking. So that is Perpetual on its own. But we're also gonna defend or make good support to that through the strain gauge information. Section N4, which is basically the thinnest of all of them, the 4 inches of AC sitting on top of 5 inches of CCPR, that was observed for 4 research cycles, so 40 million easels in total. But we started seeing the first evidence of cracking close to the end of the 3rd research cycle, which is the 30 million easels. And in the next 10 million easels of application, it basically it fell apart. And we're also going to talk about how the strain information is looking on that particular section. So if you remember from the last webinar, and just to give you an understanding, the green, blue, and red lines or that you're seeing are measured strain information at the bottom of the CCPR layer, right? Because that's where the crack or the bottom of fatigue cracking is going to initiate, if it has to initiate, because that is the most critical point through bending and tensile strain at the bottom of the CCPR layer. That's where you will see the crack happening. And we do have strain gauges at the bottom of the CCPR layer, or between the CCPR layer and the granular base. And the black line, what you're seeing is the Willis limit. It's basically the distribution of the strain. At the end of the day, if the data or the strain data is falling onto the left side of that line, those sections are gonna see bottom of fatigue cracking after a few million of acyls. And if that line is falling to the left side of the curve or left side of the Willis limit, that is where those are the sections that are never going to see bottom of fatigue cracking. And but the question is that Willis limit again was developed for the granular base material. That was not developed for a recycled base material. On top of that, that Willis limit, whenever all the base asphalt layers where the bottom of cracking initiates, all those are conventional HMA layers, right? That material is a conventional HMA layer. But here, when we talk about the CCPR layers, this crack initiation or the critical point is a CCPR layer. And we don't know whether that Willis limit is going to hold true because you're translating all the way from HMA, which is much more flexible material than CCPR. Probably that's the wrong statement to use, but in terms of the cracking issues, we need to limit still hold true or not if we apply the same limit from a HMA derived limit to a CCPR section itself. And it's telling the same story, right? If you see the section S12, the measured strains are falling to the left side of the Willis limit. And this is exactly the section which we saw no cracking. And we basically started identifying that as a perpetual section because the strains are so low that that strain is basically never initiated any crack in that section. But if you see specifically the N4, which started cracking and fell apart in after 40 million acyls, this is the section that had highest strains at the bottom of the CCPR layer and falling to the left side of the Willis curve. So at the end of the day, the conclusion here is Willis limit is still holding true for a CCPR of perpetual pavements to design using a CCPR or cold recycled base layers. But let's dive deep into what's happening with that N4, or are the cracks that we saw in N4, are they just the surface cracks or the bottom of fatigue cracks, right? Because that's the definition of a perpetual pavement is bottom of fatigue crack should not happen, not any type of surface cracking. So again, what's happening with that N4 or what happened to that N4 between that 30 million or 20 to 30 million to 30 to 40 million, those two research cycles at the end? So if we see, so we have vertical pressure plates between the CCPR and the aggregate base. And if you see the vertical pressure over time, so those four different clusters, what you're seeing are basically each one is corresponding to each research cycle, all the way from 2012 to 2021. And if you see, especially from 2018 to 2021, you basically see a big jump or a big jump in the vertical pressure. That definitely means there is compromise happening with the structural integrity of the layers sitting on top of that pressure plate. So that only could happen through basically deterioration or structural damage of that layer or layers above that, which are CCPR and AC layers. But if we see based on basically the temperature side of the story, again, it's telling the same thing. The blue and the black dots there corresponding to the first two research cycles. And in those two research cycles, no damage is happening. But if you start seeing the 2018 data and the 2021 data, the 30 million acyl, that is where you see higher vertical pressures. That's representative basically of some kind of cracking that's happening within that pavement. But after 40 million acyls, we basically trenched that section for a forensic investigation. And the layer that you're seeing, the flat layer here, is basically the ag base. Brian, correct me if I'm wrong. And the layers that you're seeing on the cross section are basically the HMA and the CCPR layers. And that's the pressure plate data, what I was talking to you about before in the past slides. This is where the pressure data, what I was showing you. But again, that's our better days before cutting or before went through that saw. But again, the cross section that you're seeing, the direction of the traffic is this way. So whatever you're seeing is not the width of the pavement. This is along the longitudinal direction of the pavement. But if you start seeing that, those cracks initiated at the bottom of the CCPR layer and found their way all the way to the top after close to that 30 million acyl mark. So there is clearly the bottom of fatigue cracking happening with that section N4, and Willis limit showed the very same thing, is that that section is going to fail in bottom of fatigue cracking. So again, it's a good conclusion to draw that Willis limits still hold true even for CCPR layers. Again, that's only data from two sections, S12, which was perpetual, and 4, which was not. But we need to have more data to confirm whether we can use the same Willis limit for designing perpetual pavements with CCPR or recycled materials. But again, at the end of the day, what we learned from these 3 test sections: one, S12, the section S12 with CCPR plus FDR layer, which was found to perform perpetually because we never saw any kind of subgrade rutting or any kind of bottom of fatigue cracking on that section. And that being said, as I said, only with the limited data of 2 sections or 3 sections that we have here, we can design perpetual pavements with CCPR by just using the Willis limit that was developed for conventional flexible pavement cross sections. And section N4 was still performing well. I would not say that performed badly. It saw 40 million easels before falling apart and 30 million easels before it actually saw any kind of crack initiation on the surface or crack propagation to the surface. But again, it fell apart between that 29 to 40 million easel range. This meant basically the section is not perpetual because that was confirmed after the forensic investigation of trenching the section, and clearly can see the bottom of fatigue cracks basically found their way up. And if you guys want to learn more about these 3 particular sections, because I said like these sections were there from last 13 years or there for like almost 12 to 13 years. And these are the 4 NCAT reports where you will find a lot of information about these 3 sections in terms of the performance data, IRIs, and your crackings and ruttings, but also mostly on the structural side of the story, the back calculated moduli, the strains and stresses, and how and explanation behind how these sections were performing. And that's all I have. I'm going to hand it over to Brian.
All right, thanks, everybody. Good morning, good afternoon. Maybe most folks are here in the morning. Again, my name is Brian Diefendorfer, and I work for the Virginia Transportation Research Council. That's the research agency or research division for the Virginia Department of Transportation. And I'm here to talk a little bit about what we've done with the technology and things that we've learned from NCAT. So the research basis for the designs that we used on some of our real-world test sections came as a result of what we learned at the NCAT test track. And again, if you look at the concept of perpetual pavements, we're looking to minimize the asphalt strain, the tensile strain at the bottom of the asphalt layers. And one way we could do that is by putting a stiffer foundation beneath that. Rather than using maybe just an aggregate base, we might stabilize that aggregate base in an FDR process to increase the stiffness of that layer. Why are we interested in doing this? From an agency perspective, we're interested because we have seen, and the theory for perpetual pavements is that if you can remove the distresses happening from the bottom of the pavement, they're much easier to fix distresses that happen within the top of the pavement rather than having to dig down within the pavement and fix it in the foundation. So we're looking for longer lasting pavements, and we're looking for pavements when they do start to deteriorate, they're things that we can address more easily from the surface. Walking back through some of the things that we've done leading up to the work we did at NCAT back in 2011, we had a section of I-81 reconstructed. It's about 3.7 miles long, where we used FDR and CCPR in the right lane to rehabilitate that, and then CIR in the left lane. Since the distresses were less in the left lane, we did a less intensive operation. That section is continuing to carry traffic to this day. Really no maintenance action has done there other than sealing longitudinal joint the last year or two. And it's carrying somewhere around 8,000 trucks per day. So we're accumulating about 3 million easels per year on this section. So again, from 2011 till now, we're probably 30 couple million easels on this section. Some of the performance information that we've collected is showing rut depth and ride quality numbers. Our rut depth information, we're seeing rut depths less than a tenth of an inch over the section. This data is up to, I think, 2024, so 13 years of testing. And then the IRI, we're in the upper 40s to mid 50s inches per mile, depending on which lane for these sections too. So we're seeing really good performance out of these sections. Again, this is testing in the right and left lane, so slightly different processes were done in each. The work that we did on 81 back in 2011, we were really focusing on materials characterization at the time. And so we did a lot of laboratory testing from the materials that were collected during construction, but we didn't have a good idea of what was happening internally within the pavement. We're still, having to address the performance based on surface observed condition. And so that kind of led us into sponsoring the test sections that NCAT this area helped to introduce. And the 3 test sections that he mentioned were, again, S12, N3, and N4. And I'll focus a little bit more on N4 and also on S12. So if you look at these two, again, S12 and N4 being basically the same sections, except for the presence of that stabilized FDR foundation in S12. As Siri showed, the strain values were very, very low in that S12 section. So again, looking at this, we started to think, hey, maybe we've got an opportunity here to build a recycled test section, or excuse me, a recycled pavement section, but also a perpetual pavement section made out of recycled materials. And when you start to look at the cross-section of what we did there on the S12, the asphalt layers were made out of two layers of SMA. So the top layer had 12.5% of RAP, the second layer of the SMA had 30% of RAP, and the CCPR consisted of 97% RAP and 2% foamed asphalt, 1% cement, so 97% recycled material. And then the FDR layer there had 4% cement, so it was 96% recycled material because it consisted of the existing aggregate base and top part of the subgrade from there. So if you look at this entire cross-section, we created a perpetual pavement section using 76, if you take the averages, 76% recycled material for this pavement section. It was really something, a unique concept at the time when we did this work. It probably maybe still is a unique concept, but it's something we've learned a lot from, and we've taken that concept here and we applied it in different locations. And that's where I'll head to next with the next several slides. Partway through the second test cycle that we had there at NCAT, we were seeing really good performance data, especially that S12 section. And about the same time, the agency was starting to look at some widening work on the Interstate 64 on the eastern side of Virginia. Interstate 64 at the time was a 2-lane facility from Richmond, which is kind of here in the center of the state, where I-95 and I-64 cross, heading towards the coast and port areas. And so there's a lot of traffic related to the ports that go through this section. And it was existing concrete pavement built in the 1960s in 2 lanes, almost all the way down to Williamsburg, about where the arrow is pointing. And the agency was looking to do some widening and reconstruction on this section, adding a 3rd lane and new full width shoulder to the inside. And based on the work that we came up with, or we saw with the 81 project from 2011 and the NCAT work starting in 2012, we pitched the concept, maybe we can incorporate some of these ideas into these projects. And it turned out that the contractor was allowed basically an alternate bid, and they were able to choose which design they wanted to go through, a conventional or this recycled concept. And the contractor chose the recycled concept for both of these projects. So the widening work was done in 3 segments. Segments 2 and 3 had the recycling concept. Segment 2, the length of that project was 7.08 miles. For segment 3, it was 8.3 miles. And the work was done in the eastbound and westbound directions. So when you count the existing lanes and the new shoulders and the existing shoulder and all that stuff, you can multiply each one of those lengths by 10 to come up with the lane mileage. So segment 2 was about 71 lane miles. Segment 3 was a little over 83 lane miles. Again, the project scope for this work was to add a new left lane and new full width left shoulder. And then traffic was shifted over to those new travel lanes, or those new lanes, and then the existing pavement was reconstructed and a full right shoulder was added. Again, the concept here, this was an alternative design based on the ideas we had from the ID1 project and from the NCAT test sections to use this combination of CCPR and FDR. If you look at the 2 ideas we had here for the original design, the original agency design was this thicker asphalt structure over top of an open graded drainage layer, and then a cement treated aggregate layer, which is a plant produced material. It's produced aggregate base, mixed with cement, produced in a pug mill, and then brought out to the site. Was replaced with this idea of this alternate recycling concept. If you follow the AASHTO 93 methodology, the structural number is very similar. Thinner asphalt layers replaced the base mix of the asphalt with a CCPR that was produced from existing RAP stockpiles. Again, the open graded drainage layer concept, and then the 12-inch stabilized foundation, which was the contractor had the ability to use either recycled concrete aggregate or RAP to produce that FDR in the lanes to the inside that were widened where there was no existing pavement, material didn't exist previously. Material was brought in and then processed in the FDR process, and we call that a imported FDR. And then the 12-inch FDR in the existing lanes is just a traditional FDR because then once the concrete was pulled off, it manipulated the existing aggregate base and top part of the subgrade. So a little example, here's some of the FDR work that was done, some of the picture of the RCA aggregate that was used. And again, the reclaimer was here showing mixing the cement in with that material beneath once it was added. The CCPR material consisted of a combination of wrap and then screenings. And the screenings in this case were number 10s, which we found really good success using. We had a fine graded mix 100% of it past the 12.5 millimeter sieve. In terms of the mix design for the CCPR, it consisted of 2% foamed asphalt and 1% cement. The CCPR here was produced in a cold mixing plant located near the project site. When this picture was taken, I was standing on top of the unprocessed wrap stockpile, and the stockpile that you see in the background here in this picture in the upper left, that's the processed wrap stockpile. So they used quite a bit of material on this project. And then you can see the picture there in the bottom right. It was all paved and brought out to the project, paved with conventional paving practices and conventional materials. In addition to the work that we did on I-64, we were actually able to go through and do some instrumentation work as well. We really followed a lot of the concepts that the folks at NCAT are using on the test track, and we got a lot of help from the folks at NCAT at the same time on how to set this up. And so what we wanted to look at were those different performance areas that I mentioned in one of the first couple of slides. We wanted to look at the strain at the bottom of the asphalt layers. We also wanted to look at pressure on top of the drainage layer and on top of the subgrade. So what we found through the instrumentation work that we did, we would go periodically, maybe once a quarter, and weigh dump trucks that were loaded with sand or gravel or whatever the local VDOT office had handy. We would weigh the trucks and then run them over top of the pavement sections over different temperatures, and then we would start to plot the results. And what we found is that the strain values from the I-64 projects and these blue circles at the bottom, we actually had a lower strain value than we did from the NCAT test section S12. If you remember, that was considered to be a perpetual pavement section with strains in the 130 to 140 microstrain neighborhood. We're actually measuring strains in the I-64 project down to 30 and 40 microstrains. So we would expect to see really good performance of the I-64 section, but if you look at the space in between these two lines, there's probably some room for optimization of the pavement design for that I-64 section, meaning we probably could have made that section perhaps maybe a little thinner and then still seeing the perpetual performance like we saw with the NCAT section S12. We monitored this section this is about 3 or 3.5 years, and recently published a VTRC report on the work we did on I-64. So this slide is showing a summary of kind of what we did, 81, S12 to I-64. This is the sequence chronologically how we went. But what I really want to point out is the concept that was used here. We're using a stabilized foundation in terms of the FDR underneath this CCPR, the recycled layer, and the concept really held true across all three of the sections using that concept and using that process. And I think it's a really good design and a really good technique to use for pavement rehabilitation or lane widening even if the materials are available. So Federal Highway also published a report where they looked at our I-64 project, series of projects, and came up with some information. This report I don't think is available online currently, but if you're really interested in looking at it, I'm happy to send a copy to you. Feel free to email me about it. But they show that VDOT saved approximately $15 million using these processes. Again, these are large projects, so large quantities here. Used more than 360,000 tons of wrap and about 1 million tons of recycled material in total. And some of the LCA work that they did too showed that we reduced the total primary energy demand, or the amount of energy created to produce the paving materials, by between 25 and 45%, depending on the processes that they analyzed. And as a result of that, reduced the global warming potential, or the CO2, by 15 to 40%. So some significant numbers on these things. We've also taken these concepts and then extended them a little bit further, looking at some ongoing lane winding projects that we have, again, on I-81 and I-64, slightly different locations, but same routes. I-64, there are 3 contiguous segments going from Richmond that butt up to the recycling projects I talked about earlier, about a total of 28.4 miles, where we're doing a lane widening with FDR in the foundation, using again the idea of the recycled concrete aggregate to create the FDR, so that material is brought out, spread. The stabilizing agent this time cement again was used and spread, and then it was processed just like an FDR, existing FDR. So again, we would call that an imported FDR. Interstate 81, right now there are seven separate projects. I think there are 2 that are under construction right now. 2 or 3 have been awarded but are not under construction. Another 2 or 3 that are to be advertised. And if you add all those up, it's about 29 miles worth of work. And again, here we're using FDR, but in this case, it's a slightly different flavor. We're using FDR solely created out of number 10s. And I'll walk through that process here in just a few more slides. So the number 10 screenings, the folks in our aggregate industry talk about it as a code-generated product, meaning that the number 10s are produced when we're looking to produce something else. And so again, it's not a waste product, but it's something that's produced at the same time as something else that we're looking for. So there are a lot of good properties using this material. We're seeing unstabilized CBR values around 60 something, 65. And we found out that when we stabilize that with cement, that by adding 4% cement, we get a mixed design and compressive strength of about 400 PSI, which is kind of right in the middle of what we're looking for our FDR designs. And so the folks in the district in this area have been really progressive on promoting pavement recycling work, and they started to look at this as an opportunity to perhaps produce a lower cost but still high quality material. And so they selected to go with this. The contractor made a mixed design, everything passed our specifications, and so we're allowing this to move forward. In terms of the placement, the material is spread via a grader and a series of dozers and then compacted and then stabilized in cement, but it still follows our FDR specifications. So we would still classify it really as a imported FDR. We have a lot of screenings available in the quarries around us. And between these series of projects, these 7 widening projects, we're expected to use somewhere around 334,000 tons of this material. Just showing a couple photographs here of some of the quarries around that area. There's a lot of this material that's available to be used. In terms of placing the number 10s and stabilizing them with the FDR equipment, it looks very similar to any other FDR job that you've seen. Again, this is showing the the number 10s that are underneath the equipment here. The cement has been pre-spread out on top of this, and then the reclaimer is going along and doing the blending work. And so in this photograph, you see the live traffic that's moving to the right of the equipment. That's the existing lanes of Interstate 81. And this machine is operating in what will be the future left lane, and there will be a future left shoulder beside this. And all that will have this FDR material underneath of it. Again, the folks in this district have done a lot of work in helping to promote these concepts. And one of the things they did is also they looked at some life cycle cost analysis, looking at the present worth, and they analyzed a few different designs. For this case, the FDR design that I mentioned as we're building it, was the base case. And the original pavement design that could have been used here, consisting of more imported aggregate materials and thicker asphalt layers, came out to have a cost difference of about plus 19% compared to that FDR alternative. We did find that if we were to analyze and look at a FDR plus CCPR alternative, that we probably could have saved about 10% had all the materials been available. But on this side of Virginia, there's not a lot of excess wrap to make that CCPR. And so for wrap to be brought in, it would have had to have been hauled in, and it would have eaten up most, if not all of that, almost 10% cost savings that we could have gained with the CCPR. So that design process was not followed. And so again, we stuck solely with the FDR. They also did a cost analysis looking at continuously reinforced concrete pavement, and the cost difference for that was about 28% higher than this FDR concept that we used. So if you take all these different segments and put them together, the district estimated a potential cost savings for all the segments of a little over $25 million. And that's the last slide I have. I'd be happy to address any questions either here or by email later on. And again, thank you so much for attending.
So perpetual pavements, Surrey touched on this as just kind of one of the definitions and the purposes of them. They're designed to prevent bottom-up fatigue cracking and structural rutting perpetually, in perpetuity. Traditionally thought of as being done using hot mix asphalt and some type of aggregate or a granular base. However, it can also be done with alternative bases. And the tools that we use, specifically the Willis limit, that we can use to design perpetual pavements, these tools also work with alternative bases as well. And Surrey did a great job talking about that. I really appreciated, Brian, your focus on FDR and CCPR as sort of as different tools for different purposes. And I loved your comments about how FDR is a great tool to be used for lane widening on interstates. I know you've done some other presentations where you talk about the staged construction and the ability to kind of keep traffic moving while you're doing lane widenings. But developing a very, very strong outside lane. And imported FDR, as Brian was calling it, it really solves two problems. It can be used to improve roadbed strength and develop perpetual pavements, but it also utilizes quarry fines, and that's one of the things I love about the idea is it's something more sustainable and using up these materials that we got to find somewhere for them to go. So with that, this is a great time for us to answer any questions you may have.
All right, so I got a question real quick I wanted to ask Brian, because I've not seen any come in here, and I want to make sure, even if you did cover it, I want to talk about some of the savings that you guys feel like you realized with, the single project on I-64 with that widening, because I saw some of those numbers in the past, and I think it's great for this group to even hear it again.
Yeah, so again, we documented some numbers that have been in some TRB publications, and we estimated about $15 million cost savings, again, across those two segments. Now, again, that's a big number, but the projects were big too. So, but there's significant cost savings with trucking, because you're not hauling so many materials in and out, especially when you're able to stabilize things in place. Also, it's less expensive to use, 100% wrap than it is to use 100% hot mix. So there's cost savings there. And again, one of the things I wanted to mention that we, as an agency, we don't really track, but is there, is the environmental savings. And again, that FHWA publication documented a lot of that.
Yeah.
Those are some things that we don't do, because again, it's not something we have a process for that in place, and we don't look at it as a criteria for our payments, but it still exists and it's still there, and it's something that needs to be considered as well.
Okay, great.
Brian, I've got a question for you. I'm sure you're familiar with the rejuvenated CCPR sections that we've got on the off ramp, and there's a few of those around. What do you think is kind of the future of high performance CCPR mixes?
Yeah, I really think the work that you guys are doing on that rejuvenated mixture may be it. So the mixtures that I talked about with the CCPR all require some sort of surfacing. And so on a higher volume section, it may be multiple lifts of asphalt. It may be a single lift of asphalt. It may be something like, a chip seal or a cape seal, something like that, depending on the traffic volume. And we've had some experience in all those ranges with some of the recycling work that we've done. But to get to the point, to me, kind of the holy grail of this recycling concept is you got your FDR stabilized foundation, your CCPR goes on top of that, and then maybe you've got a rejuvenated CCPR that goes above that to where it doesn't need some sort of surfacing applied to it. And I think really that's where we ought to be aiming. That way we can really look to optimize the amount of recycled material used and optimize the recycling throughout the pavement structure top to bottom.
Yeah, we've got, I think, about 5 sections out there right now that have, I think, 4 inches of CCPR and then a 1 inch of a 475 thin lay. But then we have one section, I think Surrey may have mentioned it, 5 inches of CCPR, polymer modified emulsion, but it's the final surface. So we're actively monitoring that and seeing how it handles seasonal changes and stuff. So there should be some more coming about that in the future.
Hey, Brian, I really liked the part where you were showing the microstrain values from the sections that were here in Alabama that Virginia sponsored, and then the microstrain values that you guys have seen on 64 that dropped so much lower. Both of those being perpetual pavements. Do you have any sense for how thin you think that this section could be? I think that's a shot in the dark. I realize there's, we need to back calculate and figure and probably test, but just what your gut feeling is.
I haven't gone through and looked at it in that way. I don't know. So, it's a combination of what is technically possible and what folks are comfortable with. So what
Right.
we did there at NCAT, when we started that work back in 2011, we had a lot of comments from not a lot of comments, but some comments from other agencies. I can't believe you spent money doing this because this will never work. Or, my goodness, that's so thin that'll never last. And,
Yeah.
the information that Surrey showed said that, yeah, it can work and it can last. I don't know if, for us, our typical interstate pavements on the asphalt side tend to be in that 10 to 12 inch neighborhood with an aggregate base or a treated base beneath that. It's, again, maybe 8 to 10 inches, something like that. And the sections that we did at NCAT, we had about 8 or 9 inches of asphalt and 5 or 6 inches or so of that treated foundation beneath of it. So much thinner pavement sections. I think that could be a place we could go with it. I don't know if anybody, again, technically, I think we can do it. Are folks comfortable with that level and at that risk on the interstate system? I'm not sure we're there yet. I'm not sure most folks are there yet, but certainly I think the concepts flow through. And I think as time goes on and we do more of these types of pavement sections, I think we could look at different ways to optimize that.
Yeah. I like that discussion, and I think that there's really space in this discussion as well for really pushing towards that perpetual, right? I mean, that's the focus of what we wanted to do today, but at the same token, it's such a responsible way for people that are managing our road networks to design that pavement is to go ahead and make it be something that we expect to last 50 or more years with just resurfacing or pavement preservation on the surface in order to be good stewards of the taxpayer dollars, in order to be resource responsible, use the recycled materials, which you guys in Virginia have mountains and mountains of RAP, maybe not such the case in Kansas or South Dakota, but this is another tool that people can have in their toolbox to manage these networks.
Yeah,
Well, thanks
absolutely.
for,
And if I could add to that,
Yeah.
some of the work that we did on these lane widening projects, yeah, we were bringing RAP in from existing stockpiles. As Surrey mentioned with the cold in place recycling, there's a lot of things we can do with CIR to do the same process and manipulate that material in place, and to be able to do the same thing. And there's something we've talked kind of around the water cooler here at the office about looking at imported CIR, where you could take and mill off, let's say, the CIR, go through with FDR and address the foundation, and then lay that wrap back over top, and then blend it with the CIR equipment, just like it had always been there. The equipment doesn't know the difference; it's just the material that's there. And so you could do that same kind of concept. And so, someplace that doesn't have a lot of existing wrap, and they want to stabilize the foundation of existing pavement, that's a way to do it. Especially if you don't have to haul the material very far, then you really minimize the trucking. Think if you've got a plant far away from a project, 30 or 40 miles, and you're hauling a lot of material back and forth. It's a lot of fuel that's being used for that.
Yeah. Yeah. Yeah.
well, Brian, thank you so much for joining us today. It's always great to hear you talk about your expertise in this area. So
Thank you so much for the opportunity to talk.
yeah,
Appreciate
absolutely. Travis, why don't you close us out?
Absolutely. So want to make sure that everybody knows that if you come to our website, which is ncat.us, you click on the test track across the top tab there, and you can find the icon that says findings. That'll take you to all of the research reports that have been written in clear back to the year 2000 on the NCAT test track. And it's a great place to go and pull those and find information on some of these historic projects. Always want to put a little bit of a plug out there for our Training in Your Pocket program. We've got some new videos out there. Would be great if you guys would like to pop on, watch those, subscribe, share them with your friends that you think could use them, or your coworkers that could benefit from watching those short videos. And then next month, same time, same place, the third Thursday next month will be September 18th. We're really excited. We're going to talk about the use of high wrap and rejuvenators together in mixes. We're excited for our lineup there. We've got Dr. Nam Tran from here at NCAT, and we've got Dr. Stacy Diefendorfer, who Brian might know, that is going to come from Virginia TOT and talk to us on that side. So given that, we appreciate y'all joining. We'll see you next time. Nathan, last word.
Yeah, it's good to have you guys, and looking forward to the other Diefendorfer next month.